Alright, so we're going to be talking about today a motion on a ramp. An object sliding down a ramp. It could be sliding down a ramp to the right, or if the ramp was going down and to the left, then it would be moving down to the left. We're going to be focusing in on the situation where the object is moving down to the right. And the ramp itself will be defined by angle theta, where theta is between the ramp itself and the horizontal. So there's a couple things that we need to notice first. First of all, we're going to deal with a situation where this is a frictionless ramp. So there's no friction. Eventually we'll get to the point where we do handle friction in situations involving friction, but that'll be on the chapters that deal with forces. One thing that we can notice here is that the motion of this object is restricted, or it's constrained to only move and accelerate along the ramp. In other words, if we compare this with free fall, the object would just be falling straight down and accelerating at 9.8 meters per second squared the entire time. But here, this object is going to be accelerating due to gravity, but not the full 9.8 meters per second squared, because as we can see here, the ramp is restricting or constraining or sort of preventing the box from falling at that full 9.8 meters per second value. So how much it is, how close that acceleration is to 9.8 meters per second squared is going to depend on this angle over here, the angle theta. If theta is very large, we've got a very steep ramp, then obviously the acceleration of the box is going to be very close to that 9.8 meters per second squared. If the angle is really small, if this ramp would be really shallow, then our box may accelerate maybe at only 1 or 2 meters per second squared. So it's going to depend on that theta, and what we're going to do here in this video is to see what that relationship is. Another observation that we have is that both the velocity and the acceleration vector are down the ramp. So that leads to a couple of problems. If we draw our traditional x and y axis up here as x-axis completely vertical, and the y-axis, or sorry, x-axis horizontal and y-axis vertical, then the velocity and acceleration are both going to have an x and a y component. And the motion itself, as mentioned a second ago, is one-dimensional. The motion is really just going down the ramp. So if we have our axes like this, and the object of the motion is like this going down the ramp, then we've got an x and a y component of everything, of displacement, of velocity, and of acceleration, and that ends up honestly just getting kind of messy. So what we have the freedom to do is we can choose our coordinate system, our x and y axis, our x and y number lines, just whichever way we want, whatever orientation makes the problem easier. So what we're going to do is we're going to tilt the x-axis so that it is along the ramp. You're like, what do we mean by that? Well, so for instance, if that's the ramp, we're going to make that the x-axis. And of course, perpendicular to it is the y-axis. And what that does is that makes this previously two-dimensional problem where we had an x and a y for everything. Now we just have a one-dimensional problem. An object is just traveling along the x-axis, along the x number line. So it simplifies this problem immensely. We still have to deal with acceleration and what is that acceleration value. So we'll redraw this picture, be a little bit more precise now. There's our ramp. There's our x-axis. Perpendicular to that, we will make our y-axis. You can see we've got angle theta. Here's our object, our box, whatever's sliding down this frictionless plane. And then what we'll draw is we'll draw a perpendicular there so we can see what's going on. And the only force that's acting on this object is the force of gravity, which is causing it to accelerate straight down. However, as I mentioned earlier, that that acceleration, the only part of that full 9.8 meters per second squared is actually affecting the box because the ramp is preventing it. So that acceleration vector we can draw into its components. It's a sub x and it's a sub y, where you can see the x is along the x-axis and the y is the vertical. So next thing we're going to do is draw, note that this angle right here, we're going to call it phi, and this angle right down here, this acute angle, we're going to call that alpha. And we're going to notice that phi is equal to 90 minus theta. And you say, well, how in the world do we know that? Okay, let's go back over here to our picture. And over here in the picture, you can see we're going to draw, extend this acceleration vector downwards, so that we are, and we're going to focus in on this right triangle right here, where we've got theta in the bottom right, phi in the top left, and you can see that obviously phi is going to be 90 minus whatever theta is. And then to think about what alpha is, we will redraw this picture right here, this little small right triangle, where we've got phi on the top, alpha in the bottom there. And we can see that obviously alpha is 90 minus whatever phi is. So looking at those two statements, whatever phi is 90 minus theta, and alpha is 90 minus phi, so obviously they're complements of each other. We can conclude that alpha must equal theta. If you just throw in some numbers real quick, you can see what's going on. So for instance, if you imagine that theta is 30 degrees, then phi must be 60. Well, if phi is 60, 90 minus 60 is 30, so alpha must be 30. So whatever theta was, which was 30, is the same thing that alpha is. So that's the purpose of that, those equations right there. So over here I'm going to draw that picture just a little bit larger. There's alpha, and we'll redraw it now, labeling it theta, and phi at the top right. And if we noticed earlier that this top portion is ax and this leg is ay, the hypotenuse is the acceleration due to gravity itself, a, or in this case, if you're on Earth, 9.8 meters per second squared. So then we can just write some trig equations. We can say the cosine of theta is the adjacent over the hypotenuse, so ay over a. Multiply both sides by ay, so we have a cosine theta equals ay. Since on Earth the acceleration a is equal to g, 9.8 meters per second squared, so we have ay is g cosine theta. And then we'll go and do the same process for ax. So the sine of theta is opposite over hypotenuse, so ax over a. Multiply both sides by a, and we get a sine theta equals ax, which means that ax is equal to g sine theta, where obviously g is equal to a, that acceleration due to gravity. So these two formulas right here, this is the acceleration perpendicular, which doesn't really do anything, but this value right here, the acceleration in the x direction, that's the acceleration that the object is traveling. So this value right here, g sine theta, is very, very important. So wrap things up here. Ax is the acceleration down the ramp. Now this is, like I said, a very important concept. This formula, a equals g sine theta, is implied in every single ramp problem. So they're never going to say, oh, and the acceleration is equal to g sine theta. This is something that you're going to be expected to know. Just like in every single free fall problem, you're expected to know that the acceleration in the vertical direction is negative 9.8 meters per second squared if you're on Earth. And so that's implied in both of those situations. So once you know this ax equals g sine theta, then every ramp problem basically just turns into a one-dimensional motion problem. And if you always make down the ramp positive, then your acceleration is going to be positive. So, and obviously if we were going in the opposite direction, you could change your origin, you could make it positive or negative, you just have to be consistent. So, alright, there you go. Enjoy doing some problems with motion on ramps. Thanks for watching.